So I think it's a really exciting time for timber at the moment. This is some of the tallest timber buildings which have been built across the world in the last 10 years. Now, I think, even 5 years ago, who would have imagined that today we would have 3 or 4 buildings made of timber 20 stories high? So what I'd like to do today is ask the question, why is this happening? What are the challenges and what are the opportunities? Now, I thought I'd start on something a little bit more modest. This was actually the very first timber building I worked on. It was actually an old cowshed in the north of England. Durham University needed a new student bar, and they thought this cowshed would make the perfect place. Now, I think you can imagine that's got a timber roof trusses. Just where I've ringed in red, we couldn't actually see the end of those roof trusses because they were hidden inside the brickwork. And so we thought it would be a jolly good idea to take down the brickwork to expose the end of the trusses and check they were in good condition. And this is what we found. So that white line on the left, that marks where the face of the brickwork was. And you can see that all the wood hidden inside the brickwork was actually completely rotten. That hole in the middle is where I actually managed to punch my hand right through. So this was quite a lesson for me. This was actually the first existing building I'd worked on, first timber building I'd worked on. Building looked absolutely fine. All the timber I could see was fine. And yet hidden away was this hidden damage. And this was a roof which within a few weeks would probably have collapsed. And I think there's a really useful lesson here for wood, because if we keep wood dry, it really can last forever. But if we let it get wet, as here, then there's perfect conditions for the rot, the fungus to survive, and it can deteriorate quite fast. So here's an example of a well-designed wooden building, and I show this because this is probably the oldest wooden building in Europe. It was designed just before the French invasion. We get on pretty well with the French these days, but 1,000 years ago, relationships were a little bit choppy. This guy called Norman the Conqueror came over. This was built, I think, about 10 years before he crossed the Channel. And you can see that the walls of this church are completely made of wood. What you're looking at are trunks of oak trees, and it survived 1,000 years because that wood is kept dry, overhanging roof, lifted up off the ground on this sort of brick plinth. So I think that's the really good news. Wooden buildings can survive forever if we keep them in dry conditions. There is a challenge with wood, and I think one of the biggest challenges is that it grows in these rather awkward shapes and sizes. And if you think about it, these trees are not even cylinders. These are actually slightly conical. And so if we want to use that wood efficiently, then we have to cut those trunks into fairly short lengths, maybe 5 or 6 meters long. Otherwise, there's huge amounts of wastage as we cut off these sort of tapering pieces from the sides. Now, short lengths of wood, 5 or 6 meters long, was fine actually if you happen to be a 13th century Cistercian monk and you wanted to build yourself a barn. In fact, I rather like the idea that this barn was used for 700 years until the 1960s for its original purpose as a barn. I think for me that's a true example of sustainability. But as I say, if you want to build much bigger structures, and by the mid 1800s, people wanted to build these big new railway stations, these sort of the airports of their day. What you happen to be looking at there is King's Cross Station. I think that's probably platform 9 3/4. So how can you get these small bits of wood to span a big space? So what you see first of all on the left is the original architect's drawing of King's Cross. And what you're looking at is actually a timber arch. I've just shown you the image at the top, how that's put together. We call it a bolt laminated arch, short lengths of wood with staggered ends bolted together. Now, in fact, eventually that roof was replaced with wrought iron, but originally it was indeed a timber roof. That was, I think, 1849. Now, you can imagine that making an arch in that way is very labour intensive, and also that arch member isn't very strong because there isn't a terribly good shear connection between all the planks of wood. And so if I show you Paddington Station, built by Brunel, literally a couple of years later, you can see that it was, and in fact still is, entirely in wrought iron. And so overnight, wrought iron, and effectively an early steel, has become a much cheaper, stronger way to span the large space. Now, obviously a much better way to make those arches, those bolt laminated arches I just showed you, would have actually been to glue planks of wood together. That's a much stronger way to join pieces of wood together. But the real breakthrough didn't really come until the Second World War, because until then we did have wood glues. I mean, even the Egyptians had wood glues, but these were glues made of milk or based on fish, and so these organic glues were not waterproof, not great if you want to fly through the clouds. And so come the Second World War, 1930s, here we see the mosquito, one of the very early uses of these new waterproof wood glues. And the detail on the left there is actually a detail of one of the wings. You can see this tiny little glulam beam. And so that's great. You know, we've now got waterproof wood glues, because even if we're going to keep our timber building dry, everything always gets wet during transport, during construction. And so having waterproof glues is incredibly important. So now we can take those short 5 or 6 meter long pieces of wood cut from the tree. We can cut, as you can see on the left, we can cut fingers into one end, and we can join 2 sets of fingers together to make a nice strong finger joint, a nice long length of glue loaded in shear. Then we can take those short lengths of wood, we can take those planks of wood and we can pass them through a glue curtain. So what you're looking at is you're looking at glue and resin and hardener, and the resin and the hardener get mixed on the surface of the wood. So then we tank those planks and we clamp them together overnight until the glue has cured. And of course, while the glue is still wet, as you can see here, we can actually very easily curve those planks and make a sort of curved beam. And so what's rather nice in wood is that we can make a curved glued laminated beam for about the same price as a straight beam. Now, another challenge of wood is that there's a hugely variable strength. This is about 500 planks of wood, all of the same species, probably many taken from the same tree. And you can see that there's this huge variation in strength. If you look along the bottom, the seemingly identical planks of wood can vary in strength, maybe by a factor of 4. Now, there's a pretty obvious reason for that. Wood has knots. The knots are simply the remains of the side branches plugged into the main trunk. And I think you can imagine that those knots almost are rather like holes. And so if that hole, like in the bottom image, if that hole is towards the bottom of the plank, bottom of the member, then that's massively going to reduce its strength. And so it's these natural defects that means that we get a huge variation in strength. The idea I love is that you can take the log of a tree, you can chop it up, and you can glue all those pieces back together again in a random order. And because they're in a random order, those those defects don't go all the way through. And so we actually end up with something stronger than we started with. And we can actually be even cleverer. We can take the pieces with lots of knots and we can put them in the middle where the beam is not working very hard, and we can take the clearer pieces with smaller knots and we can put those on the outside. And so we're starting to make for ourselves a much stronger, more predictable strength sort of member that we can use for engineering purposes. So glulam, laminating, gives us the ability to make not only much larger members, but also much stronger members. This here is actually the largest glulam beam I've ever seen. And what I've done, I've compared it against a typical Arup engineer. Arup engineers tend to be about 1.5 to 2 meters long. And this particular glulam beam is about 40 meters long. There's a nice story here, actually. This is actually Jane Nixon. Jane is now back in our Sydney office, but at this time, Jane and also Mike King were over from Sydney, over in London, and they were responsible for the design of the aquatic centre with Zaha Hadid for the London Olympics. And at this stage, we were exploring doing the roof of that aquatic centre in timber, and we made this visit over to Austria when I took this photograph. Now, wood has always been a very large part of the construction market, but to be honest, it's been for pretty small buildings, 1 and 2 story houses, and really all the houses in North America. I know a lot of houses in Australia built like this. A very efficient form of construction, uses a very small amount of material, but really quite weak. The big change we're starting to see is wood used for bigger and bigger buildings. And so, as I say, the question I wanted to ask today was, why is this happening? Now, I think there are really 3 reasons, 3 technological developments which have happened. The first is CNC fabrication. We took this photograph in 2005. That's only 15 years ago. Now, at that time, this was the only computer CNC fabrication in the timber building industry. Obviously, what it gives you incredibly accurate cutting. We can cut members to within about plus or minus 1 millimeter. Now, every timber factory has one of these. This was the building that we were building 15 years ago, and it was a temporary pavilion that we did with Alvaro Caesar, Eduardo Soto de Moura, and every single piece in that roof is different, 459 different pieces. There's absolutely no way that we could have built that roof without CNC fabrication, and we really couldn't have done that economically in any material other than timber. Now, the second development is the invention of CLT, cross-laminated timber. This, I think, really simple but clever way of making these huge panels of wood from small planks, simply by gluing those planks together in this sort of cross-laminated fashion. Now, CLT is not a new idea. It was invented well over 20 years ago, but it's only been cheaply available for perhaps the past 7 or 8 years, to the point at which we can actually afford to use it in buildings. And the final innovation is really modern connections. These screws, you can see those screws are self-tapping their way into the wood. And each of those screws can carry about a ton, something like the weight of a car. So the idea that we have really strong connections means that we can make our timber structures much cheaper. And so if we add all these developments together, the large CLT panels, very accurately cut out to shape and then quickly, strongly joined together with these self-tapping screws, we have the idea that a wooden building becomes like a giant piece of flat-packed furniture. This was a 40-meter long sculpture that we built with Alison Brooks Architects. And the important thing about this is that this 40-meter long sculpture was assembled on site in about 7 days. Not only in 7 days, but incredibly quietly. What you're looking at is, it was an old barracks, but it is now a university courtyard, and all the lectures were still going on at the same time as this was being built. And I think it's no coincidence that as well as residential, a huge amount of the timber construction that we're now seeing across the world is actually for educational buildings, schools, universities, simply because that construction can carry on in the quiet at the same time as the buildings are still being used around. So now I've told you that what timber really gives us is speed, and that speed feeds directly through into costs. So what I'm comparing here is the costs of a typical concrete building on the left and a typical wooden building on the right. Now, the red bar at the bottom, that shows the cost of the structure. This is fairly indicative, but it's typically the case that a bare wooden structure might be 5, 10, 20, 30% more than the basic cost of a bare concrete structure. But because that wooden structure, it's prefabricated, it can be assembled so fast on site, we have between 10 and 30% program savings. And of course, those time savings on site mean that there are big savings in labour costs. And very often we can also leave the finishes off and leave the wood exposed in this beautiful way. And that also means that we save in the time and cost of putting on finishes. And so what we've been finding is that the total cost of a completed timber building is now very, very similar to the total cost of a concrete or in fact a steel framed building. And so we can really see how wood is now starting to compete. And of course, this is if we were, say, building an office, this is before we take advantage of the fact that that office building might be available to start renting out 3 months earlier with an extra sort of financial incentive for the client. So from about, I would say, 2010, 2012, we start seeing multi-story timber buildings, entirely made of CLT panels, being built across the world. Even relatively remote locations such as Melbourne. So on the right we see the 40 Tower, built by Lendlease, and you can see how that is entirely made of floors, walls, entirely made of CLT panels. This very quick, accurate way of building. Now, of course, that's great if we want residential, small cellular spaces. We can also use wood for larger open plan spaces. In that case, we would combine it with an open framework. That framework could be in glulam. I quite like the idea of actually using a steel framework. So here we have CLT floor slabs, nice, quick, dry construction combined with a steel frame, also fast, dry construction. And we can also combine our timber with concrete. So this is another interesting idea, which is the idea of what we call a timber concrete composite slab. And but by doing this, we can get away, because a lot of the strength is added by the wooden downstand beams, so we can get away with a concrete slab which is perhaps only 10 or 12 centimeters thick for what might be a 10-meter span. And so by combining the advantages of the two materials, the strong light wood and then the massive concrete, we end up with a composite panel which has got very similar properties, similar strength, stiffness, similar dynamic vibration performance, similar thermal mass to a solid concrete panel, but only sort of half the weight. And I think this tells a lot about the future of timber. Yes, we can do buildings which are completely made of wood, but I think the future is actually using all the materials to their advantage, combining wood with steel, with concrete, to get all the best advantages of all the materials. So, as I say, I think you can understand why we're now seeing wood used for bigger and larger and more ambitious structures. The interesting thing is that our building design codes, our timber codes, were really written 30 years ago. They were written for small houses like the one we see on the left. They were written for fairly simple roofs, like the one on the right, just a very simple 3-pin arched beam. So we're in this interesting time when we're trying to design much bigger, more challenging structures, but the codes we're using were really not written for the sorts of structures that we want to design today. And of course, the other difference is that whereas 30 years ago, a timber structure would always be designed by a timber specialist. Today, every architect, every engineer wants to build in timber, and that's great. But it means that we need codes which are suitable for that. And I think in many ways, and I don't want to shock, but I think in many ways there are parallels between timber today, where we're seeing it used for taller and taller and larger buildings, but there are real parallels with precast concrete in the 1960s. Now, precast concrete, I think, is a great way of building, but in the 1960s, it very much got ahead of the codes. And people were building bigger and bigger structures. And of course, this was until 1968. And in 1968, there was a small gas explosion inside somebody's kitchen in a building called Ronan Point. And that led to this partial collapse of the building. And I think, what that did was it meant that nobody then used precast concrete in the UK for another 40 years. I think one of the challenges with engineering is that we design for very, very extreme events. Strong winds, heavy snowfalls as here, the earthquakes. And so if we've sort of if there are unsafe aspects built into our designs, it can take a long, long time for those to become apparent. And so this, as an example, this was the ice rink that collapsed in Germany in 2006, on top of literally hundreds of children, and quite a few were killed. And I think what's important about this is not the particular specifics of why this particular roof collapsed, but is that after this, every single timber roof across Germany was checked, and problems were found in hundreds of those structures. And I think this is just an example. This is no criticism of wood whatsoever. It's just in any new method of construction, it can take time for safe methods of design to be developed. And so that's really the challenge for us, or certainly us engineers, is how can we innovate in a safe way? Now, this was a meeting that we had in our office in London a couple of years ago, and this was a gathering of some of the top timber engineers from across Europe. Each country has about 2 representatives, and this is the committee which is writing the new timber Eurocode. And so across the world, there is huge research effort going into developing new codes to enable safe design of these much bigger timber structures that we're now building. Now, I think one of the big challenges for engineers, I mean, most of us, we're much used to designing in steel or in concrete. And of course, wood is a natural material. And that means it has very, very different properties. This that you see at the bottom image here, that's a microscopic image of the wood fiber. And of course, if you think about, what's the function of a tree? The function of a tree is not to be cut down so that we can turn it into buildings. The function of a tree is to, and the function of the trunk is to get water from the ground up to the leaves. And so we can imagine that trunk like a bundle of drinking straws. And of course, a bundle of straws is incredibly strong if we stretch it or squash it parallel to the straws. But across the width, it's really quite weak. We can pull those straws apart quite easily. And so it's this sort of material which is 5 or 10 times stronger in one direction than the other. Now, one of the implications of that is that wood is very brittle. So this is a test that I watched. I saw this happening in Munich, and this was a test on a particular timber connection. And that connection was being sort of, if you like, stretched, pulled apart. And you can see how it's failed. But the important thing is not how it's failed precisely, but the fact that when I watched this test, there was absolutely no sign that it was about to fail. It was carrying the load quite happily, and suddenly there was a bang, and it snapped. And that's this incredibly brittle behavior that we get in wood. Now, as engineers, we're much more used to working with ductile materials like steel, something that bends quite easily like a paperclip, rather than the wooden matchstick which snaps. And even when we're working in reinforced concrete, obviously concrete itself is a brittle material, but the reinforced concrete codes insist that we under reinforce our concrete sections. We don't quite put in enough steel, so that it's mostly the steel which fails first, and so we still get a ductile failure of that steel. But that's the difference in wood, where we're actually working in a more brittle material. Now, for about the past 10 years, it's really exciting. We've had lots more computing power, and that enables us to design more and more complex structures. And those structures have really become so complex that there are multiple different load paths. The bird's nest is just one extreme example, but it's a very, very common situation. And multiple load paths, so that we know that the load path that we can see in our computer model is never going to be the same load path that the real structure out there uses. But it doesn't matter, because we can be confident that the steel will behave in a nice ductile way. And so even if the real structure finds a slightly different load path, it will slightly start creaking in places, and it will all the connections will very slightly in a ductile way help to redistribute the load to other areas. But of course, if we're working in wood, and if all those connections are quite brittle, then they don't have the ability to mold and bend in the ductile way and redistribute the load. So we have to think really in quite a different way about how we design our timber structures. Now, another aspect of wood being cellular is that it's incredibly efficient. It's incredibly lightweight. Weight for weight, it's better than steel, and a huge amount better than concrete in terms of its weight compared with its strength. Now, of course, that's really useful for transport, but it means that wooden floors are much lighter than concrete floors, for example. And if we think that force is mass times acceleration, like Newton told us, so if we're walking across a floor with a certain force, a certain weight, if the mass of the floor is smaller, then the acceleration, F equals ma, the acceleration is going to be much bigger. And of course, acceleration means we can feel the structure vibrate. And so a wooden floor is always governed by vibration. In fact, a wooden floor will tend to be much livelier than a concrete floor for that reason. So what you see here, this is actually us doing some vibration testing on a particular wooden floor. We were actually designing a gym, so we really had to get this right, because people would be there with heavy weights and jumping up and down. And the results of that testing and the lessons from that, we have been feeding back into the new Eurocode that's really going to be to make sure that the performance, so that now we can really predict very accurately how timber floors are going to behave. Yes, timber in principle is more lively, but we know how to design it accurately, and we can make sure that we design it so that performance of those timber floors is acceptable. And on the right, you can see some of the computer modeling that we've also been doing to accurately predict how those timber floors behave. And I guess the final aspect of wood being natural is that, of course, it's a hydrocarbon, and it does actually burn. This was a test which my colleague David Barber over in the States was involved in. There was quite a consortium involved in this testing, and this was actually, you're looking through the door into a CLT lined compartment, and you can see how starting from the left, the fire is slowly dying down. And then what happened in this instance was that that particular CLT had been made with a particular glue which softened under heat. And so what's happened by the photograph on the right is the glue's softened under heat, the outer layer of char has fallen off. So partway through the fire, we get this fresh face of wood exposed. And the fire, you can see, has reignited. Very similar effect to what we get when we put a fresh log on an existing fire. And then that room then carried on burning really until all the wood was consumed, and until the structure collapsed. Now, if the sense that wood carries on burning like that is really, if we're designing a relatively small structure like this was a 4-story office that we built in London. And those, you can see those really quite chunky glulam beams and columns and quite thick CLT floor slabs. The great thing is that although wood burns, it actually burns at a very slow rate. And so this wood, almost without this structure, almost without trying, it has about an hour's fire resistance. It will stand there quite happily for a good hour. And obviously, for a small building like this, where it's an office, so people are not asleep, they can escape relatively quickly because it's low rise. The firefighters can fight all the fire from the outside of the building. So that's good. That means that building is, the fire safety, life safety of that building is really good. But of course, if we compare a much bigger structure like this, this is actually a residential building. So 19 stories residential. People might be asleep. There might be elderly people in there. There might be children. Obviously the firefighters can't fight the fire all from the outside. They actually have to go inside to fight it. And so it's really important that building stays standing safely for a much longer period. And so we need to think about that in terms of how we safely design our timber structures. Because of all these challenges of wood being a natural material, fire, floor dynamics, brittle behavior, we really need to stand back and we need to rethink how we do our structural design. We need a completely different philosophy from the philosophy that we use for steel, from the philosophy that we use for concrete. Now, just to give a few examples, really, this is the Metz Pompidou art gallery that we built in France with Shigeru Ban. And the Shigeru based, very, very clever idea. He based the entire building on the hexagon. You can see that on the right there, the overall shape of the roof is hexagonal, protecting these 3 sort of concrete tubular art galleries. And you can see in the middle how the whole roof, the weave of the roof was sort of inspired by a traditional Japanese hat. That was on the top right is Shigeru's only model. So the whole building is based on the hexagon. Really clever idea because of course, France itself is, as you can see top left, is an absolutely perfect hexagon. That, of course, is why if you live in France, you refer to France as the hexagon. It's remarkable that God should have made a country which was so perfectly hexagonal. And so, this was really felt to be a building made for France, and was just one of many reasons why Shigeru won the competition. Now, Shigeru also made this statement where he said the design of this building might look quite complicated, but it's really very simple. Now, of course, architecturally, it's a lovely, simple idea with this roof over the galleries. I do have to say that from an engineering point of view, it probably is one of the most complicated buildings we have had to design. What you're looking at is our computer model, and here was a roof which couldn't quite decide if it was a shell, working rather like the shell of an egg, like an arch or a dome, or if it was a catenary hanging between, like a chain hanging between the central lift shaft and the columns around the edges, or in fact if it was a beam working in bending. In fact, what we found was if we changed one of the small assumptions and stiffnesses somewhere in this model, the whole sort of load path would change. And so the reason that this cost us so much to design was that we had to explore multiple different load paths just to make sure that we didn't accidentally break the wood somewhere in the brittle way. This is a detail of one of the connections. You can see how the different layers of wood are connected together with this giant timber bolt. And you can also see I've dotted there in red on the left how we put in some what we call cross-grain reinforcement. This was simply some more of those long self-tapping screws I showed you. And the idea was that if you yank sideways on that big wooden bolt, we didn't want that to split sideways out of the wood. So we put in those long screws just to get a more ductile behavior out of the connection. But of course, on most projects, we can't afford to spend what I think in that case was probably a couple of years doing really, really complex analyses. We need to work with the material. We need to come up with appropriate designs. And so this is quite an exciting project. This is recently opened. This is currently the largest timber roof in the UK. Each of those square panels that you can see measures about 15 by 15 meters, just to give you a feel for the scale of this. And this roof covers, I think, more than the area of a couple of football pitches, something like that. And now, what you're looking at is, of course, a grillage. And if we were designing a grillage in steel or in concrete, we would rigidly fix all the members together. But of course, as I've just told you, if that in timber would be creating quite a complex, indeterminate structure. We wouldn't know where the load was going. We'd have to make sure that we didn't accidentally break one of the connections in a brittle way. And so that really, like when I said, we have to completely rethink how we design buildings. Look how this was put together. This was not actually put together as a two-way grillage. We turn this into a one-way spanning structure. And so you can see that we've essentially got beams cutting across the corners, and then long diagonal beams running between those, and then all the short pieces that make up the grillage are simply small infill pieces. And so we've made a one-way spanning determinate structure. We're telling the load exactly where to go, and so that's very easy to design because there's only one load path, and also it's much cheaper to build because it's much cheaper to make all the money in a timber structure. Really, all the money is in the connections, and so we want to minimize the number of connections. We want to keep the connections as simple as possible, and so we go for a nice simple one-way spanning structure. Now, I think another good example of really designing a structure to tell the load where to go is this project. So this is what we call the smile. I showed you this under construction earlier. This was actually an idea from Alison Brooks, and the brief from the client was to come up with really the most ambitious CLT structure ever built. And because what we wanted to do here was, this was going to be the first ever use of large hardwood, tulip wood CLT panels, and we wanted to really find a structure which expressed the strength of those large panels and of those large panels in tulip wood, in hardwood. And so Alison comes up with the idea of this sort of smile shape, which essentially means you've got two really, really long cantilevers. People can go inside, and so you can get lots of weight people at the end of those long cantilevers. Now, I think you can imagine when 60 people run inside and they all run up to one end, then the whole thing wants to tip. And so we need to pull it back downwards to the left with that red arrow. Now, at the same time, of course, it wants to snap, and it wants to snap in the middle of that weakest point where the doorway is. So there's a lot of things going on right in the middle. And if we home in on the middle there you can see the doorway. Underneath in black, we've got what was essentially a wooden box filled with steel counterweights to stop the whole thing tipping up. And now you can see on the left there, we've got two sets of these long screws. First of all, ringed in blue. There's one set of screws which are to take this horizontal sort of push-pull load going above and under the door. So those take the load from the wall or from the floor back into the wall, if you like. And then ringed in orange, there's a second set of screws there. Those are now vertically aligned screws, and those are the screws to take this vertical push-pull to stop the whole thing tipping up to tie it down to that box. Now, there's actually quite an interesting story here. You can see that wooden box in black there is really, really shallow. And that's because just below the ground was the remains of the Millbank prison. That prison was, in fact, this is an aerial photograph of the prison. As you can see, this sort of hexagonal shape. And you can really see the size of it if you compare that to the size of the Thames to its right. And I think what's interesting about the Millbank prison is that if you were say you'd stolen a loaf of bread or something like this, and for this terrible crime, you were going to be transported to Australia, never to see your family again. then this is the prison in which you were kept until you were taken down to the river and taken off by ship. And something like 150,000 people went through this prison and then off to Australia. And when we built the Smile and we excavated down about less than a metre for our wooden box foundation, was the first time in 100 years since it was demolished that the foundations of the prison had been exposed. And in fact, we found ourselves sitting right on one of the corners, one of these sort of corner turret stair towers that you can see at the bottom of the image. And so why we were forced to have such a shallow foundation, because this of course is one of the blacker periods in Britain's history, but is quite an important now ancient monument, and we weren't allowed to touch it. That's my favourite image taken inside the Smile, and it was like this wonderful view, sort of looking down the tube, and a pattern of light, the sort of sunlight coming through from the other end. Alison had this great idea of putting these holes in the walls. You could sort of go and sort of spy on people outside, and put your hand through the hole, but they also let the sunlight in, which sort of moved across as the sunshine moved across. Really clever project. And so, as I say, we need to rethink how we design our timber buildings. We need to be designing appropriately in this sort of brittle material. We can do hugely complex sensitivity analyses, like we did on the Met's Pompidou roof at the bottom, but that really costs a lot of time and money. It's much better to work with the material, as we did top right with the that roof at Warwick. Create a determinate structure. And of course there is a third way, and the third way is to make the structure behave in the ductile way, like we do with our concrete structures. We under reinforce them, and we make sure that the steel always fails first, so we can have weak nailed connections in our timber structure, as you can see top left, and we can make sure that those nails fail first. And of course that's what we do in our lightweight timber frame houses. When we nailed the plywood or the OSB to the studs, we had lots of small nails. Those nails are the weak points, and those structures behave in an incredibly ductile way. It's why timber houses are so great in an earthquake, because they've got all these ductile nailed connections which can absorb lots of energy as the building shakes. Now, what about the other challenges I talked about with wood? The fact that it can burn easily, or it's very lively, and we get more vibrations. I often think that as engineers, we sometimes, if we were left to our own devices, we would really come up with very boring buildings. We would come up with 4-story high shoeboxes, and we really do rely on architects to challenge us. And in this instance, Team 5 Architecture in Amsterdam challenged us and said very simply, we would like to build the tallest timber building in the world. It's quite a simple challenge, and we like challenges. So so we thought, well, what's a sensible way to design a tall timber building? First of all, we didn't want actually lots of small cellular spaces. We wanted a building which was going to be very flexible, so that in the future it could be adapted. And also, we wanted to free up the facades. We didn't want that sense. We didn't want to design a timber tube with lots of small windows. We wanted nice big glazed facades. And so what we thought we would do was we would concentrate all the CLT into those party walls, those main walls between the apartments. So that's the thick black lines you can see here. And what that gave us was, it gave us some nice stiff shear walls to start resisting the wind on a building, because a tall building is often governed by dynamics. We don't want it to be, we don't want to be at the top of the building and when the wind blows, feel the building vibrate. It just feels rather uncomfortable. And so that's what we did. Also to make those walls even stiffer, we didn't, if you're doing a low-rise CLT building, we do what's called a platform frame. That's what you see on the left. So you build a wall, then you build a floor slab, then you build another wall on top and another floor slab. Very quick, simple way of building. But of course, that wall is not going to be terribly stiff, because those floors can get squashed very easily. And so to make that wall a lot stiffer, what we did was, as you can see on the left, we've actually, each wall panel sits on the wall panel below, and then there's really a lump of concrete between. And so that wall is now nice and stiff. And that gives us another advantage as well, because what we do is, as you can see, the CLT floor slabs, we stop and start the CLT floor slab either side of the wall. And what that means is that the floor vibration can't be transmitted across from one side to the other. So this is what I mean about designing in a different way, rethinking how we design. Now, those, I have to say that those CRT walls were still not stiff enough for 20 stories. And I think it's pretty obvious that, CLT comes to site in small panels. And so when the wind blows, you get very small movements, opening and closing and sliding of those joints between the panels. And that really reduces the overall stiffness of the building. And we simply couldn't make this building stiff enough to be comfortable for the end user. And so what we did there in red, we put in a concrete core. And I have to say, I really have no problem at all with mixing and matching materials. I do think that every material has advantages and disadvantages. It applies to wood, it applies to steel, it applies to concrete. I do think if we're going to do a tall building above about 10 stories, there is nothing better than a concrete core or a steel core to stabilize that building. And what about fire resistance? This is I told you this is it's a tall building. People could be asleep. The fire brigade are going to have to go inside to climb up the building to fight the fire. So it really needs to stay standing for a long time. And so we did some fire tests. And this is another test on a CLT compartment, which we did this time in the UK. And what we managed to show is that if there is only one surface of CLT exposed, and in this case, as you can see on the left, it's the ceiling which is exposed, and if that CLT is made with a nice, good heat-resistant glue, and there are more and more heat-resistant glues which are now available, then that's just to make sure that the char doesn't fall off partway through the fire. So if there's just one CLT surface exposed, then what we've shown is that fire will die down, and once all the contents of the room have stopped burning, then that CLT ceiling surface will also stop burning. And that's because for wood to burn, there needs to be instant heat on the surface to drive off the gases, and it's the gases that then burn. So if there's because there's no instant heat, because all the contents have stopped burning, so then that CLT ceiling will stop burning. It's just like if you can't just have one log burning on a fire. You need embers, or you need two logs or something like this, so that each log can keep the other log hot and keep those flammable gases coming off. And so that's what we did. We've limited the exposed wood. Although the whole building is made of wood, really, apart from that concrete core, we've limited the exposed wood to just one surface inside each compartment using a heat-resistant glue to make the CLT. And that means that those fires will die down, and that building is therefore safe in fire. So, out of everything I've said, just to really conclude, what is my view of the future of wood? And I think the biggest market for wood is still the sort of the low-rise buildings, roofs, and the great thing about these is that they're still need fire resistance, but generally not nearly so much, and so we can often leave the wood fully exposed. As you can see here, and so we get this great thing of timber as combined structure and finishes, and the fact, this might be, say, a 6-story building or something like that. The fact is that across the world, most of what we build is low-rise buildings, and so there's a huge market out there in which we could use timber. Now, I think timber also works well for lower-rise residential buildings, perhaps up to about 10 stories, the sort of height where, as I say, you can still use your CLT walls to stiffen the building for the stability of the building. and so that you can really build the entire building out of say CLT. Now obviously for these multi-occupancy residential buildings, we need really good sound separation between all the apartments. That building really needs to stay standing in a fire. It's a residential building, it's a much higher risk building. The firefighters are going to have to go inside to fight the fire. It's got to stay standing in a fire. We can't afford it to collapse. And so really all that CLT, it might be the structure of the building, but it's all going to have to be, or most of it anyway, have to be encapsulated so it doesn't take part in the fire. So encapsulated for fire reasons, encapsulated for sound acoustic reasons. But a good way of building for perhaps say a 10-story residential building. Now, I think if we want to build more than about 10 stories, and do it economically, then what I think is that we should be combining timber with other materials. As I say, the best way for a stability core is to really make that out of concrete or steel. Really the best for the columns is, we want to keep our columns as small as possible to maximize the amount of floor area. And so it makes sense to use a stronger material, really like steel often for the columns. And so I like the idea of these sort of hybrid structures. So incorporating wood into our bigger buildings, perhaps just in the floor plates, and if we think about it, if we can incorporate wood in the floor plates and perhaps halve the amount of concrete in the building, that's still a really, really big win from an embodied carbon point of view. And so let's think about hybrid structures combining all the different materials using the advantages of each. Now, I think just to finish, I would say that a good timber building doesn't just need good engineering, it also needs a good architect. And your architect, your engineer need to understand the material. And in this case, we wanted to build, this was going to be the world's first ever structure in hardwood CLT. So we picked this lightweight wood called tulip wood from North America, and because it was an experimental structure, we were limited to these very tiny little CLT panels. And so DRMM architects came up with the idea of gluing those little CLT panels together in the factory to make these preformed flights of stairs. And we had these flights, and then the idea was that those flights could be reconfigured in different configurations. And that was why they called it the endless stair, because the idea was that it could be endlessly reconfigured. And so we built it, as you see here, in London, and then we rebuilt it in Milan in a different configuration, and then we rebuilt it again in Zurich. And so really, really clever idea, really understanding the material. And I think here you can see how when I say you need to understand the material, this shows how the entire geometry of the structure grows out of the raw material. We need to minimize wastage, and so our raw material is 1 inch, 25mm thick planks. So we plane those planks down to 20mm, and so 3 of those planks glued together make 60mm. So 60mm is the thickness of the CLT panels that we use to make the wall of the stairs that you can see on the left. If we glue 2 planks together, then we get 40mm in the middle, and so 40mm is the size of these posts, which was effectively our balustrade to stop people falling off the side. And then finally, if we glue 5 of those planks, or rather even 8 of those planks together, I can't really add up, we get 160. And so 160 was the exact height of the treads. So working with wood is all about working with the raw material, minimizing wastage, and therefore minimizing cost. And as I say, this tulip wood, this was the first time ever that this had been used structurally, the first time that it had been used to make CLT. And so we needed to do some testing. We needed to prove that it was glueable. And in fact, tulip wood is in fact very easy to glue. We needed to do tests in rolling shear. So that's the test that you can see on the right, where the middle panel we're trying to push out. And you can see that those interlayers are sort of all the fibers going into the paper, all those interlayers are sort of rolling and failing in rolling shear. And then finally, we had to test it, because I think you can imagine that CLT, with the being cross-laminated, is really a very, very complex material. And it's, on the scale of an overall structure, it's really impossible to accurately model it. We simply haven't got the computer power, and so we had to have a simplified model. And so we then did a test on one flight of stairs where we loaded it up with these steel weights, as you can see in the middle, to compare the deflection and the strength of that against what had come out of our computer model. And I'd just like to leave you with my favourite image of the endless stair. Of course, we built this in London in September, and so apart from the first day when I took this photograph with a blue sky, every other day it rained. It was there for about a month. At least I got one decent photograph. But why I love this is I think this is just a perfect example of combined architecture and structure. I do think wood is this amazing material. It really has a huge potential to be a larger part of the market. And that's really what I'd like you to think about when you go away today, is which of your buildings, it won't always be suitable, but which of your buildings could timber be suitable for? Think about it as an option. But as I say, like every material, just like steel, just like concrete, timber has pros and cons, advantages and disadvantages. And the challenge for us as we push timber to greater heights, to larger structures, is to make sure that we understand the material and that we innovate in a safe way and create safe structures for the future to demonstrate what an amazing material this is. So thank you very much, and I hope that leaves you with some inspiration to go off and design some timber structures of your own.
Well, thank you, Andrew. That was most interesting. I found that fascinating. And isn't it great that we are, even though we're in lockdown in Melbourne and dealing with COVID around the world, we're still able to see presentations like this. So thank you. Now we'll go to the panelists now. And before we get into the questions, just want to ask the panelists, do you have any comments to make on the presentation?
No, Jennifer, it's Alex Edwards here. I just reiterate your thoughts that it's a really exciting presentation, and because it's a really exciting time to be involved in timber buildings.
Yeah, I don't know whether I have too much to add to the presentation. I think it certainly sets out some of the key components. One of the things I find interesting that came up on a project today is just the understanding of the timber as a material and as a product, and how that drives the decisions in form. So really that close relationship between architect and engineer very early on is when you get the best timber projects.
Yeah, absolutely. Robert, do you have anything to add before we jump into questions?
I do, quickly. I think it's a great presentation. Really nicely sort of put, and really nicely and quite simply set out the challenges of timber. And I think Andrew has touched on it there, that it's timber projects, timber buildings are very much a coordination exercise between architects and engineers, but also between different engineering disciplines. So particularly fire, structures, acoustics, you know, it's a very big coordination exercise that we need to undertake early on in the design and fairly rigorously as an integrated team.
Yeah, definitely. The key is getting in there at the conception period and you know, spreading the experience of the likes of Arup and our other fantastic people in this space to encourage more development and more building in timber. So Rob, one of the questions I'll direct to you. How do timber construction for medium and high rise overcome FRL requirements in Australia? And that question's from Peter. Yeah,
well, straight in there with probably the main issue for fire engineering. But again, as I say, this is a coordinated effort. So the answer to this really is between fire and structures. And I don't think it's a case of overcoming the FRL. It's a case of demonstrating that it's met, or at least the equivalent is met properly. So the building code, the building regulations, and what's reflected in the building code allow a building to be designed so the structure will resist fire to the necessary degree. So we need to determine the necessary degree. And I think Andrew's presentation touched on that very, very, very nicely, very clearly. For a sort of a 3 or 4 story office, the necessary degree is a lot lower in onerousness than a 20-story tower. So at some point we need to design absolutely for burnout for the more onerous, complex, larger buildings, but for smaller buildings, then there's more room for flexibility. Can I just add as well, I understand there's probably a wide range of disciplines on this, so I'll try not to make it all about the fire, but I think as soon as you expose timber to performance solution, and representative tests are obviously a good way to kind of feed into the performance solution, but even if you've got a test that shows that you've got an element that achieves a 120-minute FRL, then that's just part of the performance solution. You can't say because that's meeting the deemed to satisfy requirement, then it's equivalent to the code, because it's not.
Interesting. Look, the next question, Toby or Alex, feel free to jump into this one. What is the benefits of timber structures over precast concrete? From Anonymous.
I was actually composing a response during the presentation. I was going to send as a written response, but I might as well, seeing as you ask it. I mean, the key one is that the structural engineer, being lighter, does offer opportunities in the right sort of circumstances. And of course, the beautiful library down in the Docklands in Melbourne is a great example, because the lighter structure enabled use of existing the existing wharf and effectively not, avoiding need for new foundations. But a great motivation, of course, is its sustainability credentials and lower embodied carbon. And when something like 1/3 of the world's carbon emissions arise from concrete, we kind of, I think that's something in that order anyway, but concrete and cement production has a massive impact. So where as a structural engineer we can introduce timber over timber, then we really should be thinking about whether that's an opportunity available to us. There's no doubt the visual impact is of particular interest to many, not just architects, but many building users or building owners. And then indeed, there's something that I find quite interesting is how it changes our construction techniques and methods. And really, we should be, it gives us new opportunities to adopt off-site manufacture, modular design, and then taking as much of the construction processes off of sites, making those sites safer, and then enabling shorter construction programs that can then lead to other cost savings. So I just wanted to give an example. At the moment, we are using cross-laminated timber for the seating tiers within a theatre in Brisbane. It's a 1,500-seat theatre. And ordinarily, we would look at precast concrete as this for the seating tiers. But the opportunity to use timber and the fact that CLT is now available within Australia means that we can support our seats using CLT. It means that for the curved auditorium, we can have a high precision to those tiers that we couldn't achieve in precast ordinarily. It's lighter, which gives advantages to a cantilevered balcony. It means that we can also incorporate certain features into the design using CNC milling that we wouldn't be able to otherwise, and it starts to take activities off of the critical path. So, having timber available, even on conventional materials, conventional building projects, for example, gives us new opportunities in both design and construction. So for me, I think it needs to be a tool in all of our toolboxes, and evaluate its opportunities case by case basis.
That's excellent. Alex, do you have anything to
I was probably just going to reiterate Toby's point. I think one of the benefits I see is that it can suit off-site manufacturing really, really well. Timber's easier to machine and cut than steel, and with concrete, you're normally trying to minimize the number of molds and keep things standardized. We don't have quite the same constraint there. And so it starts to change mindsets a little bit about what needs to be done on site, and can you minimize that, and can you then, once you start down that path, you can actually end up with, sort of some really great benefits. Because it's lighter, you need smaller cranes, but because you're lifting in bigger pieces, that's okay too. And so you get faster and faster, and it flows into this sort of, beautiful benefit of stuff being done more and more off site. And so that it happens much, much faster on site. And so it's kind of really suited to that, as a material, really ideally suited to that kind of way of thinking.
I think absolutely, and in terms of delivering affordable housing, it has to be considered in the construction of affordable housing. So great opportunities there. Another question for Toby and Alex. Rob, you're getting off fairly lightly here. We'll have to have a look for some more questions for you. What about differential movement between the concrete core and the timber in a tall building? This is from Rufus.
Alex, do you want to jump in first? Or?
Yeah, so I think that was talking about the tall residential building that Andrew talked about. And I actually was involved in reviewing that one, and that was one of the calculations we put quite a bit of thought into. But generally what happens is, yes, the timber does move because it's a softer material, but concrete does move too. And it's all about balancing the two so that there isn't much differential movement. There wasn't any need for specifically special detailing in that one from memory, but it was kind of carefully managed to ensure that you had the, enough enough movement in both parts of the building so that you didn't get a differential. What that did come down to, though, and it was touched on a little bit by Andrew, is timber being a natural material, and concrete certainly too, has a huge variability in its properties. We always talk about sort of minimum strengths in a code, but what are the real stiffnesses, and is your timber likely to be much higher, and is your concrete likely to be much higher? And so it does make it quite a, it becomes part of the design task to really think about those things and make sure that they're considered. But I don't think it was any harder than probably considering it in any other building. I think what's special about it is that because it's a new material, everyone's thinking about things, but you kind of get to the end of them, and maybe in 5 or 10 years' time we'll not be worrying about it as much because we're more familiar with it.
Excellent. Panelists, sorry, Toby, you were going to add something?
I knew that it just serves to illustrate that part of our job as design engineers is to to identify and design out variability and unknowns. And as we go through with timber design, there are some areas that we know with some certainty and other areas that we don't. And some of that is to do with grading, approaches to grading, material variability, etc. When I've tried to when I've looked at feasibility of multi-storey buildings, I've typically tried to design out that differential feature by trying to avoid concrete. But sometimes you may be met with other challenges, and at some point or another, going down the concrete core is going to make more sense. I think one of the interesting things about the way that timber it is evolving as a construction method is that a lot of research and interest goes into developing connection details, and often you can get not necessarily highly manufactured, but you can get really careful details that are developed that suddenly remove all of that variability and unknowns to you as a designer. So there are ways of dealing with those thresholds, but I wouldn't be surprised if we start to see techniques of design and detailing that start to remove that variability, so we don't have to go through reams and reams of calculations to have a functioning core. and yeah, inside a timber building.
I'm conscious of the time. We have a few minutes left, about 3 minutes. Rob, was there any particular questions in the Q&A area that you want to address, or Alex and Toby?
Yeah, there's one that's quite important. I think I can address it quickly from Lucas. It says, how does fire perform differently between a fuel load being typically floor-based to what will now be walls and floors and ceilings? So I think that's a great question. I think, you know, pound for pound or kilo for kilo, a fuel load sort of configured on a wall or a ceiling will burn a lot different to, you know, the same amount of fuel load that's based on the floor. I think there's a picture from maybe Felix's PhD at Edinburgh that shows the same amount of fuel, but one configured on the wall, one configured on the floor, and the flame extensions out the window are significantly different. So more severe for the wall and ceiling configuration. But I think in terms of practical design, the key thing here is configurations where you have walls and ceilings together. And I think because timber walls and ceilings together, you know, that can create a re-radiating surface. And Andrew touched on it in the Hope design by saying they limited the ceiling as exposure. Now, if you've got two re-radiating surfaces, you know, like the logs on a campfire, or as Andrew talked about, and also that combined with certain glues, then I think that can lead to really sort of unpredictable fire dynamics and unpredictable fire durations, and hence fire resistance of the building. So yeah, so I think that's an important point to get across.
Thanks, Rob. Alex or Toby, we have to wind up in a minute, but if there were anything that jumped out at you that you'd like to address now?
There seemed to be a theme just touching on durability of timbers, and really just to share that what I've learned about durability is very much about spending time to understand different species of timber and how that affects your natural durability, understanding that you don't specify timber solely by a strength grade, for example, and that it's about understanding detailing and how that relates to the architecture. So spending time with your architect and understanding how connections can shed water and not allow water to build up, for example, when you have exposed connections.
Thank you. Well, unfortunately, we're going to have to wind it up there because we do have to stick to our timing. So thank you, Rob, Alex and Toby for participating in the panel. We really appreciate that. Just to talk about some upcoming topics, we have on the Ballarat government, that date's incorrect. Sorry, people. Next week we have the Ballarat GovHub case study, and you can see the upcoming events after that. Some interesting topics there. That's the design and construct process with the project team. So that'll be a very, very interesting one. Thank you for joining our webinar today. We really appreciate it. We've had a great turnout of people, and please go to our website, and there are many, many things that are useful to designers, engineers, etc. on our website. So thank you everyone for participating today, and we'll see you next week.